Hello, this is a note about use of the 2102D Starfinder to choose the best the best triad of celestial bodies to take sextant sights of. So when you go out on deck in the twilight to do a celestial navigation fix, you don't randomly choose stars. There are, three or four, or three, typically it's three, that are, or star-planet combinations that will provide the best fix. And that's what this problem's about, and using the Starfinder to do that. Now, there's other ways to do it, but this is going to be with the 2102D Starfinder, and in particular, I will illustrate that using the Coast Guard exam questions. This is a question. There's almost always a question in the celestial endorsement on the use of the Starfinder, which is interesting because this is a device that dates from 1921 in fact, and it's still in use in professional services around the world. Probably unique plastic device in that regard. So here and so the Coast Guard exam questions on this, there are basically two types, you might say three, but one is the kind we're going to do right now is there's a time and date and so forth, and it's going to ask what is the best triad of stars to make a fix with. And that's one type of problem. And the other variation of that, which is that sometimes these here are all stars. They could just as well have a planet in there. And if a planet makes it a little bit harder, chances are if there is a planet in one of the answers and you're running out of time, chances are that's the right answer. But there's a couple of them that have two planets. So that's the two types of problem. The third type of problem is actually quite a bit easier or faster, and that is they just tell you a time, and they tell you the height and bearing. You see a star out there, you've taken a sextant sight of a star, and you know its height from the sextant, and then you took a compass bearing to it, and so you know its bearing. So you got its height and bearing, and then your job is to use the Starfinder to figure out what star it is. Now that's a relatively faster exercise. This type of exercise here can in fact be one of the longer questions on the exam. And sadly enough, most of the time it takes is really not related at all to the use of the Starfinder. It's just all this intermediate stuff that we have to do, and that's what I'm going to show now. But here's an example. So this is a date, July 24th, and your 1912 zone time position is this. So these latitudes are going to always be very close to either 15, 25, or 35 degrees. This one's going to be, we're going to be using the 25-degree template. That's the only templates we have every 10 degrees. Based on 15s. So this will be 25. We'll use 25. And then there'll be a longitude, and the longitudes can be east or west. That changes one step in the process. And then it says consider their magnitude, that's how bright they are, their azimuth, the direction, and the altitude, how high they are in the sky. And with these criteria, which of these three sets of stars is best suited for a fix at, quote, star time. And they don't say anywhere what star time is, and that's one of the issues we have to figure out. Now, and so looking at this, you see 1912 zone time is basically local time. So that's like 7 p.m. local time. So it's probably not quite dark yet. It's not quite dark yet. So, but it may be pretty close. This is, we're at 24 degrees, and it's a summertime. It's probably an hour or so later, I would guess. It's real sights. But anyway, we don't know that. But here's the point. We have to check that. Star time, I'm going to tell you what that is in a minute, and that's one of two definitions, but it doesn't matter which of two they use. But this could be quite a bit earlier in the day. This could be like mid-afternoon in some of the problems. So we have to figure that out a little bit. Okay, so there you go. What's this note here? We do have practice problems at the website, at our StarPath website. for these. Okay, let me go to the next picture here. Okay, so let's talk about, quote, star time. And this picture I've lifted from our textbook on celestial navigation. It is here. The sun is setting like this, and when it's 6 degrees below the horizon, that's called the time of civil twilight. And when it's 12 degrees below the horizon, that's called nautical twilight. And these two times are in the almanac. And physically or atmospherically, in normal conditions, at civil twilight, it's dark enough to see the brightest stars. And at nautical twilight, in typical atmospheric conditions, it's too dark to see the horizon, which you have to see to do a celestial fix. So the star time is sometime between these two. They could either call it this time, civil twilight, or more, in a sense, it's more logical. We tend to, in our teaching and in our tools, we define, quote, star time, or the time you're going to do the sites or plan to do the sites. We talk about that as being halfway between these two. But anyway, that's what's meant by star time. Here's the device. 20, and look at this. These days it's fairly expensive, $85, and these are like about a foot across. These plastic rings. A diagram, and then base plate with the templates that go onto it. And it includes our purchasing a Star Path includes a copy of our textbook on the subject, on the use of this device. We do have a simulator. Available on our site. Once you've logged into starpath.com, we have a simulator, and you can use that simulator to run the Starfinder and solve all those problems, all the Coast Guard problems. And we have every StarPilot problem that's ever been, not StarPilot, but Starfinder problem, every Starfinder problem on any exams, all listed on our website there to practice with. And you can solve those with this device, with this simulator. And then they have the device in the test room, if you're going to take it in wherever they're going to give you the test. Although, so anyway, they're supposed to have one in the test room. And so that's that. So we have that. That simulator exists. That's not the subject now. So let's just look briefly at how you determine what are the best sites. There's three basic criteria. One is you want the 3 stars to be as near as possible 120 degrees apart, like that. And take a look. We have 2 references here, and I put them here. I'll put the links in the description so you can click them and go to them. But this one, oh, bummer. Let's just see if I go there. Oh, actually, it went there. Oh, that works. Okay, so what I want to show is here is a site with 3 stars. That's what it would look like if you did 3 stars 120 degrees apart. Now, the interesting thing is that's exactly what it would look like if you did 3 stars 60 degrees apart. In other words, their bearing between one to the next one is 60 degrees, not 120. You're going to get the identical looking triangle of intersections for your fix, but that's not right. The 60 degrees, the importance of the 120 degrees apart means, and that's what this article explains, it means that if you have a constant error in all of your sites, they will cancel out, and the fix will still be the center of the triangle. Whereas if you have 3 stars that are 60 degrees apart, and there's a constant error between all of them, which is a common factor, frankly, wrong index error, for example, or a particular bias on reading the dials, then that fix could be well outside of there. So that's why you want to take 120 degrees apart. The next is you want the sites to be above 15 degrees, so 10 or 15 degrees, and below some 75, 85 degrees, something like that. The low ones you want to avoid because the refraction is the main uncertainty in celestial navigation, and the refraction is the biggest at low angles. At high angles, there's 2 reasons. Once you get above about 85, the mathematical procedure that we generally use to do the site reductions breaks down. The other thing is, once they get a little higher, the sites are a little harder to take. They're harder to take because you don't know which way to point You got to be pointing at the star to take the sight. And if it's almost overhead, you don't know which way to point. It makes it a little harder. So generally, you want 120 degrees apart. You want them above 15 and below 85, say. And bright stars are better than dim stars simply because they're easier to see. Now, there's a fourth criteria which is fed into some of these analyses, and that is that they have the same height, roughly the same height. If you have to choose between two, everything else is the same, and you have two, and you have to choose the third one. Okay, you have to choose a third one. All the other criteria are the same. You would choose the third one that has roughly the same height. Now that's maybe valid. It's not a very strong criteria, primarily because the idea there is any refraction correction would be the same in all of them roughly. And the sight taking is about the same and so forth. But the refraction can actually change depending on which way you're looking. So it's a weaker criteria. Anyway, here's an article all about that. I'm sorry, I'm digressing a little bit here. Okay. So that's it. Now we have to start, let's work the math. We have to figure this out. In other words, we have to figure out what is the star time. So first of all, as I mentioned, we want to figure out the DR time relative to the star time. In other words, is that the other thing too is if you're running out of time, just assume that the DR they give you, I'm talking about, this is now just nuts and bolts of test taking. If you're behind time on working your exam, then just assume that time they gave you is a valid time. And chances are, at least at 70% of the time, chances are you'll get the right answer without doing this extra math I'm doing here. You got to do this bottom part, but okay, so we do that. Let's look at this. So first of all, we have to remind you have to get the zone, you have to find the zone description. So you take this longitude, round it to the nearest whole degree, that's 74, divide by 15, then round that to the nearest whole number, which is 5. So this is, we're at west longitude plus 5. If you're in east longitude, that'd be a minus number. Okay, so the UTC is zone time plus zone description. 1912 plus 5 is 2412. 2412. So we're talking about the actual sight time is 0012, 12 minutes into 725. 725. So now we can stop and we'll see what the actual times are as we go on. So then we have to figure, did I do these? Maybe I've done these in steps. Let me go to the next one. Yeah. Oh, okay. Oh, I do these in steps. Okay. So the first one, I've just talked you through this one. We're just finding that okay, and that's already done. Now we go to the next step where we have to find out the times, the civil time, the sunset, the civil time, nautical time. And you go to the Nautical Almanac for the date, and it's 25. Note here, too, this is another subtlety. It doesn't come up very often in the exams. In the real life, in real life, this doesn't matter that much when you're predicting these stars because you don't know exactly what time you're going to be out there and so forth. It doesn't matter too much. But just keep in mind that you have these sight times. Here, I've expanded this from here to here. But this is the sunset time, the civil twilight, and nautical. So it's dark enough to see the stars, too dark to see the horizon. So we want in this zone here somewhere. And then they give it at 20 and 30. We want 25. So we got to interpolate a little bit and get in between these two like that. But the thing I want to note is they have one set of data and 3 dates here. This always applies to the middle date. Technically, these are the times for the middle date. And then if you needed something very precise for one of these dates, like this date or this date, then you'd have to interpolate. But that's not going to be a factor in the real world or in the test room, really, frankly. At least on this type of question. So you see, you look at, so we want the setting is in between these two, that's 1849. I just add these two, divide by 2, that's here. Then these two, 10, 24, and 4, so that's 1914, and likewise over here. So we see that And the star time, really, I think the best time is halfway between these two here. So you got 1914, 1944, add those up, divide by 2, and you get 1929. 1929. So that would be the time, the UTC, that would be the UTC of star time if you happen to be located at the Greenwich Meridian. But we're 73 degrees west of there, so we have to make a correction for that. So let me go to the next one. Where is that? Here. Okay, you find UTC for DR time. Okay, so now we use arc to time. So we have to take this 73 degrees, 452, like that. And I mean 73 degrees, and keep in mind Earth is rotating 15 degrees per hour, so we have to figure out how long does it take. In other words, we figured the time if we were at Greenwich. Now we have to let the Earth rotate around so we get the time where we're located, and that's going to be we do that with arc to time. So 73 degrees is 4 hours 52 minutes. And then this 46.5 minutes, that would be 46.5. Here's the 0.5. Oh, I grabbed the wrong. Well, it doesn't matter. It's not going to matter. I circled the wrong one. Look, I technically circled 0.25, whereas we want 0.5. So this should be 3 minutes and 6 seconds. I just took the 3 minutes anyway. So it's 4:55. So you got the real star time. Now we're talking, we got UTC 0024 at 7:25 star time. Now, if we had taken what was that original one? Where am I? Let me go back to what the problem was. 1912. So we had 1912, and the real time is 00. Yeah, that probably would make a difference. 1912. Yeah. Okay. So anyway, here's the time we care about. So now we go on now to set up the Starfinder. We need to know the local hour angle of Aries, and the local hour angle of Aries. That's this local hour angle is GHA of Aries minus longitude west or plus longitude east. We're doing minus west. So we've got to go, we've got 20 zeros. Oh gosh, what was our time? 00 hours, 24 minutes. So 00 hours here on the 25th is 302 degrees, 36.9 minutes. And then we go into the increments and corrections for 24 minutes under Aries, and we got 6 degrees and 1 minute. And so always, you have to, I'll just mention it here, you got to always double check. I'm on July 25th. Be sure I'm on July 25th, not August or something weird. You got to double check at each step, or this kind of long process gets longer. Okay, so there we've got so there we've got the GHA of Aries. And now we have to do minus longitude west, and our longitude was 7346.5. So here we've got local hour angle of Aries, 234.9 degrees. Now that's all we need. Now again, with some of the problems, they give you the time. You just look this up and you're done. We had these intermediate steps to do, but now we know that number. Now we're here to the problem. We set up the Starfinder, and you picked, and again, we have an earlier video. I have an earlier video on use of the Starfinder, which we show it in our hands, and we're setting this up and doing these things, and it tells about this step. So I'm relying on a review of that earlier video to show how we got to this point right here. So now, which of these, okay, so we've set this up, and we put on the 25 degree template, 25 north. That's the closest one. We put it on the north disk, so north. And then we set this arrow in the bottom to 234.9 degrees. So just a hair under 235 right there. And this is 15 degrees per hour with time. So if you rotate this, you see these stars going up and down and setting and so forth. And so you could actually write on here, this is 0024, and then mark off actual time so you know real times along here. But that's not part of this exercise. We set this here, we're done, we put a clip on it, and then so we don't bump it. It's easy to bump these things and get thrown off. So this should be really part of your kit, one of these little clips. Okay, now, so let's look at the possible answers. FOMO. Okay, back to the basics. These are the stars in view. This is a point overhead. These are the stars right here that are right on the horizon. So in other words, this guy, Regio Centaurus, is just, 5 degrees above the horizon at this bearing down here, which looks like it's about like 180, 185, 187, something like that. These are the bearing lines here that you read here, and these are the heights going this way. So this is right overhead, and this is on the horizon. And these are all below the horizon. So you look here, here's the star Fomalhaut. There's Fomalhaut, not even above the horizon. So totally, number 1 is wrong. Number 2, Acrus. That's this star down here, Acrus. It's part of the Southern Cross. It's below the horizon. So that doesn't count at all, right? That doesn't count at all. And then let me skip another one till it doesn't work. This is number D, where this is Deneb here, and this is Vega. You see, Deneb and Vega are almost in the same direction. They're almost in the same direction. And we want them 120 degrees apart. So these two are not right. In other words, that's wrong. So this must be the right answer, we hope. So then you look at these here on the diagram, and sure enough, these look pretty good. But at first glance, these two look to be opposite each other. And that wouldn't be right at all, because two stars opposite each other, when you're doing sextant sights, are essentially the same direction, the same LOP on the page. But this is misleading. You have to read this bearing off of here. So you come down here, and this is Altair, Altair at about, this is, what is this number? 10, 20, about 27 degrees, Altair. Where is it up here? Yeah, it says 29 up there. Yeah, 29. And then the bearing here is about like 90, 95, something like that. And you can check here, the real value is 93. I'll show you in a minute where this comes from. And when you do this over here, you see that these are, in fact, about 120 degrees apart. Okay, I'm back. Sorry for the interruption. So with these, the best thing to do, to be safest, you'd read this bearing off of here and for that star, and then you could do the math and try to figure that in your head. But let me just see if I don't have, I think it's probably quickest to write down, just to write down these and make a little sketch. And then sure enough, you see that is about 120 degrees apart. And they're all bright stars. These are the magnitudes of the stars. One of those articles I gave a link to also discusses the brightness of stars and shows how the magnitude relates to the brightness. And that's that covered. This one we rolled out, it was too close. And so that's how that works. And the lead up to it is longer than the process is actually pretty, well, you'll do this whole problem faster than I did in the video. But then let me just show, okay, I'm going to wrap up with one thing here. And let me see if I have a copy of this going over here. Just to show that there is a tool. We have a tool, a calculator called the StarPilot, which is a PC or a handheld calculator or an iPhone device, and it will actually solve this problem with less than a minute, and that is because it finds it's unique among these sort of computer devices or calculator devices, and it has a feature that does calculate the optimum stars. Let me just show what this looks like over here. So you would go in here, and let's see here. You would put in, do you want to do stars only, or stars, moon, and planet, whatever. This one you're doing stars only. And then you don't even have to figure out the time. You just have to put the date, 7/25/24, and then it'll calculate the twilight time for you by clicking here. This I put in the latitude and longitude, okay. And then you say plot the sky, and then it shows what it is. And then you can say best sights, and best sites, and it will tell you it's Altair, Spike, and Alioth. And you can have various controls of how high or low the star. You can take these stars on down to much lower. I've got it set at about 10 or 15 degrees and so forth. But anyway, just to let you know that there are tools that are available that either could be considered as used for a way to test your solutions you get one way, or to actually use in practice. This is actually a popular tool for celestial navigation, planning, and site reduction, and general navigation. All right, so I'll end there. Thank you.